Okay. All right. So thank you for having me here, giving me the opportunity to talk. I will tell you about an index for the Poincare homology sphere. And this doesn't work. Okay, I'll do it. Okay, so this is based on a project I've conducted in the last few months during a stay at the Mathematical Institute in Oxford. This was done together with James Marks, and for this stay I have to thank Philip Candelas. So I've so far enjoyed this very much in this nice and friendly group. Okay, so I will tell you about what kind of index I'm talking about and what a Poincare homology sphere is and what the purpose of this all is. So luckily Nick Dory has done a lot of groundwork in explaining essentially the basics of what I'm doing. So I want to count BPS states with the so-called superconformal index, which is commonly formulated on S1 cross S3. So we're talking about supersymmetric gauge theories on S1 cross S3. Indices, they are traces over some objects that correspond to elements in the superconformal algebra. This can be rewritten in terms of some kind of gauge invariant integral that's over some objects that are essentially characters, just in the sense that Nick has told us. Yeah, so what's the property of this object? Yeah, only BPS states contribute. It's invariant under SUSY preserved deformations. It only depends on group theoretic information. It has served as an important check for supersymmetric dualities like cyber duality. That means we can compute this object on both sides of the duality. And in principle this should match, which is not always obvious. That's why we need the technology of elliptic hypergeometric integrals for that. So given two different superconformal indices that should in principle match, we can use some theorems to show that they actually do. This object is also related by localization, and this is mostly due to results in which Dagger was involved, to the full supersymmetric partition function to some prefactor. Yeah, so now what's the Poincare homology sphere? So what if we now replace this S3 by some specific quotient, namely a quotient by the binary icosahedral group, which is essentially the double cover of the isometries of an icosahedron. So, okay, by that I mean discrete rotations which leave the icosahedron invariant. And it turns out that there are 60 of them, so the binary icosahedral group is a group of order 120. Yeah. So it's also related to an interesting E8 singularity. So if one takes a look at this algebraic variety, which at the origin x equals y equals z equals 0 and has an E8 singularity, one can find this Poincare homology sphere by looking at the intersection of this variety with a certain 5-sphere appropriate size. So why are we doing this? So the original superconformal index, despite having many applications, is topologically not very interesting. So on a mathematical level, it's interesting to see how such non-trivial background geometry affects properties of supersymmetric gauge theories based on that. Yeah, especially this new index will be sensitive to global properties of the gauge theory, since this Poincare homology sphere contains non-contractible cycles. Yeah, one can derive new 4D dualities from that. One can probe known dualities with this new tool. And one can also use it to derive new integral identities in the sense that I described before. So the main technical challenge with constructing such an object is essentially the fact that the gauge theory is now based on a background geometry with non-contractible cycles, which means we will have holonomies. So think of the Aragonov-Bohm effect. We can now have states when transporting them around a closed cycle that acquire a phase. And those are holonomies, which are representations of the fundamental group of this Poincare sphere in the gauge group. So an index, which is something like a partition function, should also count those states. And yes, that's why we have to work out the representation theory of the binary icosahedral group, which coincides with the fundamental group of this new Poincare homology sphere. Yeah, we have for a start considered a very simple gauge theory, which nevertheless has some interesting results. We have worked out the representation theory for that. Yeah. Then one needs to find an appropriate counting function in the sense that Nick has told us about, that also counts these states. Yeah, this is related to an index character essentially. This was also done here. I have constructed one explicit example, namely n equals 1 SQCD with an SQ2 gauge group. I won't show you the result, it's really lengthy and consists of essentially generalizations of Q Pochhammer symbols. So it's all a mess, it's interesting to study but not nice to look at. Yeah. The next thing, that's what I'm doing right now, is I want to check dualities with this. Yes. So that's hopefully finished soon, so I expect that this will be written up sometime in summer, so you can all have a closer look at it. So the summary is, I've told you about the supersymmetric index on the Poincare homology sphere, which is both interesting from a mathematical point of view, but also might have very interesting applications for physics. In principle, what I've done here can be generalized to other gauge groups and other homology spheres. In principle, it's a straightforward process. It can just become arbitrarily complicated. So maybe there's some systematic way of addressing this, but yeah, that's to be studied in the future. Thank you.
Are there any questions?
So in your applications, you had written the application checking 4D to D dualities.
That's correct.
What is the...
So 4D 2D dualities, by that I mean consider the six-dimensional two-zero theory compactified on a Riemann surface. So that means in essential consequences, when I have a topological quantum field theory on this Riemann surface, it should be equivalent to the correlation function of this topological quantum field theory in the two-dimensional Riemann surface should be equivalent to the superconformal index of the four-dimensional part of this compactification. So essentially, I can construct a superconformal index of an n equals 2 theory, and then I can somehow show that those that I can build correlation functions of topological quantum field theory out of this. This has been studied for the original superconformal index. It has also been done for the length space, and now one straightforward generalization. We could study this also in this case where the superconformal index is a more non-trivial topology. Yeah. The interesting question here is which two-dimensional two-dimensional quantum field theory does this correspond to? How does the fact that I now have a binary icosahedral group as a quotient reflect in this two-dimensional theory? In my opinion, an interesting question to ask.
Any more quick question? Otherwise, we'll think very quickly again.